Actually, I'm Mahmoud Rasly. I'm a researcher, experimental physicist in spin running devices. Actually, I'm between Center Metallurgical Research Institute in Egypt and the Technical University of Eindhoven because I'm a medical fellow there. So today I'm gonna to talk about solid-state nuclear magnetic resonance system based on electrical spin injection technique. What I'm trying to do usually in my research, I'm trying to develop new functional devices to add new functionality for materials at parts at atomistic scale or nanoscale, and then try to use this new conceptual material into a device and see what's happening. And in my study today, I will discuss about somehow new layer structure combination between magnetism and the semiconductor in order to develop a new technique to enable us manipulating the nuclear spin in the semiconductor. Okay, so in compared to the electron spin, owing to extremely long coherence time of nuclear spin, they are considered as an ideal system for quantum computing system. Okay, for such system, nuclear magnetic resonance is used to control and manipulate the nuclear spin between 0 and 1 spin state. As you can see here, this is the nuclear spin in red, and by applying radio frequency, consider we started from the state, our steady state is like we have a nuclear spin, for example, in up direction. Then apply radio frequency, then you will be able to manipulate your nuclear spin from down spin or up spin, and also you can control all superposition state between these two directions, which is quantum computing devices. However, it is difficult to polarize originally the nuclear spin because it has a very, very tiny or small magnetic moment. Okay. Then actually, a new one is very old, very, very old physics technique used in literature, maybe like 20 years ago, but it currently recovered nowadays in order to develop new conceptual devices, as I said in my introduction. It's called dynamic nuclear polarization. In this technique, or this technique actually, instead of apply, for example, a very, very high static magnetic field to just polarize 1% of nuclear spin in gallium arsenide, just you consider you have a gallium arsenide channel. In order to just polarize 1% of the nuclear spin, then you need to apply 10 Tesla. Imagine this is very, very huge static magnetic field for application or for the device. So dynamic nuclear polarization, in this technique, we, instead of applying this external magnetic field, we just exchange angular momentum with or from spin polarized electrons through the hyperfine interaction. This technique, if you can succeed to transfer simply a spin angular momentum from a bunch of spin polarized electron like this to the nuclear spin, then you can cancel this high static magnetic field, and then you just need to apply few millitesla, which is very useful for application. Okay, based on this idea, actually, dynamic nuclear polarization, this group, they uh, succeeded to develop optical NMR system, which is have been developed, and then coherent manipulation of nuclear spin has been also observed, which is like rapid oscillation and the nuclear spin echo. Motivated by this, instead of using optical spin pumping, in my research or my talk today is dedicated to electrical spin injection. What does it mean? It means that we need to polarize both of the electron and the nuclear spin in gallium arsenide, not by optical spin pumping, by electrical spin technique. Motivated by optical spin orientation, the goal of this research is to develop electrical NMR system based on electrical spin injection technique from a ferromagnetic electrode, this four-terminal ferromagnetic electrode, namely high spin polarized electrode from Hausler alloy to a gallium arsenide channel, this blue one. And this is a very, very known layer structure of devices called the four-terminal lateral spin injection devices. It consists from 4 contacts. As you can see, we inject the current here, and then we read non-local voltage out of the closed current loop here, which is a spin products. We just like combine between magnetism and semiconductor, and we can read a signal out of the closed current loop. Okay, and the schematic. This schematic, I need to explain to you what exactly happened using these ferromagnetic electrodes and a spin filtering for the charge current injected, or a spin polarized electron will be injected to the gallium arsenide, and this process called electrical spin injection. Successful spin injection, then the electron spin will be getting spin polarized like this. By certain technique, playing with the measurement condition, we apply exactly the applied magnetic field by 5 degrees out of the perpendicular direction. Then the perpendicular component of the angular momentum of this spin polarized electron transfer to the nuclear spin. When the nuclear spin becomes spin polarized, this is the DNP, or dynamic nuclear polarization, as I mentioned in the beginning of my introduction. Once the nuclear spin becomes spin polarized, we started to apply radio frequency to manipulate between up and down spin. And from the other two electrodes here, we detect the non-local voltage, which is mean through the hyperfine interaction here, or what's happening for this non-local voltage will tell us information for what's happening between this nuclear and the electron spin under the detecting electrode. So simply inject the current here between first two and read the voltage here. What happen here in the mid of the gallium arsenide channel will be read through this detecting electrode. Okay, what we did actually, so this is the layer structure, ferromagnetic electrode, CMS, highly spin polarized Hausler alloy. This is very rich, almost 100% spin polarized at room temperature, and this is copper iron, just 1.1 nanometer. I will tell you why we introduced this insertion layer later. And this is a semiconductor channel that we grown using molecular beam epitaxial. Okay, and the point actually, this is copper to manganese silicon. It's called manganese rich Hausler alloy. It's very, very well known as a high spin source. But the thing that not so good to use this material, it's very quickly around 300, 350 degrees Celsius, then a lot of amount of manganese started to diffuse down to the channel. So in order to prevent this, we inserted cobalt iron just 1.1. And I'm sharing with you here the read pattern without cobalt iron. As you can see, our head is like amorphous, and by insertion this layer, we got very clear streak pattern, as you can see. I don't need to discuss about the device, the microfabrication. Of course, we use the lithography, argon ion milling technique, and so on to fabricate the 4-terminal electrodes. I'm sharing with you here the surface of gallium arsenide just after removing the arsenic cap before the position of cobalt ion. And as you can see here, through all of the gallium arsenide substrate direction, we can get very clear streak pattern. Okay, now I'm going to start to discuss about the measurement in order to confirm that the electrical spin injection was attempted successfully. Then you have to show me, give me evidence that you can see spin envelope-like signal, this signal, and you have to show me Hanel signal. And as you can see here, very simply, when you have a parallel state of magnetization between detector and injector, then you have parallel state, you have this resistance value, and when you have anti-parallel state, you have this resistance value. Switching the magnetization direction by magnetic field, you have this spin valve here and this valve here. That's why it's spin valve-like signal. When you apply perpendicular magnetic field, this is Hanel effect. Apply perpendicular magnetic field, then the electron spin started to precess, then the spin-dependent voltage will be dropped as you increase the applied magnetic field like this. And next slide, now up to this situation, we have a parallel situation or parallel polarization of electron spin. We will start to transfer the polarization or spin angular momentum to the nuclear spin via oblique Hanel signal. As I mentioned, we just apply the magnetic field like 5 degrees far from the z direction, then the nuclear spin started to be spin polarized like this. We have these two side peaks indicating that we have nuclear spin polarization here, which can cancel the effect of external magnetic field exactly around this value and this value at the negative side direction of magnetic field. After that, here we started to put our sample in the center of coil, copper coil. We start to apply radio frequency, and as you can see, at each resonance frequency of each nuclei inside the gallium arsenide channel, gallium arsenide isotopes and arsenic, we have three kinds of nicks or dip in the non-local voltage, referring to the resonance frequency of each nuclei here. So from time on, we will focus on manipulation of gallium arsenide 6 to 9 only. For that, we will start to sweep the radio frequency from maximum positive to maximum negative, and from maximum negative to maximum positive. And as you can see, we can see here at the point of intersection, exactly the gallium arsenide started to flip from spin up to spin down. From spin up to spin down, it means this one is the resonance frequency of this targeting nuclei. And then here, all we do, we just start to manipulate the direction of the gallium 69 by applying different pulse widths. And as you can see here, according to the pulse widths, we can get this kind of a dip in the non-local voltage, recording like rapid oscillation or manipulation of the nuclear spin between up spin direction to down spin, up spin, down spin, up spin, down spin. This is rapid oscillation, and merit, as I said to you here, we have this microsecond, maybe comparable to literature, but the most important thing, we can get this at 0. Tesla, which is very good for application. So this is my conclusion. I think now I'm running out of time, and please give me your questions.
Well, thank you very much, Mahmoud Rasly, for the very nice talk. Now the floor is open for questions. We have time for a quick question. You can either unmute yourself and ask, or simply write it on the chat.
I have to give acknowledge to my colleagues and my supervisor or my mentor, Mahmoud Rasly, in Hokkaido University, actually. So again, you can ask me any question, please.
Well, if there are no further questions, maybe we can thank Rasly again, and we